All right, are we ready to get started? Sweet. All right, hello everyone, and welcome to the Unifying Innovations and Forecasting Capabilities Workshop. Um, get started here. So, first off, I want to thank everybody for being here, both of our virtual and in-person participants. None of this would be possible without community contributions. All right, so there's me before I get a haircut. My name is Joshua Kubelnick, and first off, I want to start by telling you guys a little bit about myself. So I've been at Epic for about a year and a half now. My current position is the Scrum Master of the user support team, where our main priority is giving the community the resources they need to succeed and innovate. Um, Before Epic, I served as a weather forecaster at Offutt Air Force Base in Omaha, Nebraska. I did this for 4 years. During this time, I gained a lot of valuable insight on how the world of operational meteorology works and set me up really well for the role I'm in now. Next slide. So just a few reminders here. Firstly, part of my role as MC is time management, so I may need to gently or interrupt speakers to keep the event on schedule. Just a reminder, everyone has 3 minutes to present. And then last but not least, I want to share the theme and goals of the workshop. So the theme of the workshop this year is building a stronger UFS community through collaboration and knowledge sharing with the goal of fostering connections, accelerating contribution, and improving forecasting capabilities through training, discussion, and joint problem solving. So here's a look at our current schedule for today. Virtual poster session will be from 11 to 12:30. Training number 1, using container singularity image file to compile and run UFS global workflow on a variety of platforms. That'll be from 1 o'clock to 4 p.m. in room 2126. And then training number 2 will be artificial intelligence and weather modeling, and that'll be in the North Bay Auditorium. That'll also be going on from 1 to 4. We will adjourn at 4 o'clock today, and the hike with Allison Gregory is at 5 p.m. Slide. So on this slide, we have some QR codes and some social media tags up there. The QR code on the right is our participant guide. If you want to scan that, that'll give you everything you need for UIFCW25. Then the Wi-Fi network for our in-person participants is UCAR Visitor, and no password is required for this network. So in the spirit of all that, let's get started with the virtual poster slam. Our first presenter will be Atiya Alipour, and they will be presenting on a neural-based operator model for bias correction and forecast guidance called Narrowcast.
It looks like that person is not online at the moment.
All right. The next person is Barry Baker, Introduction to NOAA's new UFS-based operational prototype, the Global Chemistry and Aerosol Forecast System, GCAFS V1.
Hi, so I'm here today to introduce NOAA's groundbreaking new operational prototype, the Global Chemistry and Aerosol Forecast System, or GCAS version 1. This represents a significant leap forward in our ability to monitor and predict global atmospheric aerosols. GCAS version 1 is a UFS-based system designed to provide global analysis and forecasts for a wide range of aerosols, including dust, sea salt, sulfate, and black carbon. These forecasts are vital for numerous applications, from predicting UV levels to estimating surface particulate matter, to forecasting major events such as dust storms or wildfire smoke around the globe.
And Barry, you're not sharing your slides.
I'm sorry.
If you click on share in Zoom, you should be able to share your slide deck.
Can we come back, because I haven't used Zoom much.
Yes, we can move on to the next person.
Thank you.
All right, so in that case, person number 3 will be Zihong Chen, and they will be presenting investigation of data-driven background ensemble covariance from GraphCast towards hurricane data assimilation and prediction.
That screen looks all right.
Yes, you can just go full screen. There we go. Thank you.
Thank you. I'm Phil from the University of Oklahoma. So usually for an AI global model, we care about how much MSE is used. We care about how long the predictability has been extended. We care about how well the cyclone track intensity is predicted. But for our group working in
Hey,
data simulation,
Hold on one second. You're coming through pretty broken up. Give us 1 minute here. We're going to try to fix this.
That's on the user's end. Jen, do you have another tab open with the live stream or another device that we can use as a microphone?
the microphone doesn't work.
Let's do this. Let's hop into the virtual green room, and I'll be able to assist you there. You should be able to join the virtual green room at the bottom, where it says breakout. So we can move on to the next person then.
All right, the next person is Lin Cui, and they are presenting on the development of coupled atmosphere-ocean model for subseasonal to seasonal forecasting.
I'm sorry, I'm sharing my screen coming from the. This one? Can you see my screen?
Yes, we see your slides.
Oh, okay, good. Hi everyone. So I'm Lin Cui. So this work is focusing on the improving subseasonal to seasonal forecast, also called S2S forecasting. So this is a major challenge in Earth system science because of the nonlinear interactions between the atmospheric and the ocean across different scales. So this project is motivated by the potential of machine learning models to provide a data-driven alternative for modeling these complex dynamics and ultimately improving long-range forecasts. So the goal is to develop a coupled atmospheric ocean that can generate stable simulations over long time scales. So the data, we trained the model over the UIFCW replay data set, which covers from 1994 to 2016. So I will not go through the details, but so we trained the atmospheric and the ocean model individually. So then the coupling will happen in the inference model, which shows on the bottom figure. That means every 4 times of the atmospheric, then we the variables being exchanged between the atmospheric model and the ocean model. So that's it. The atmospheric time interval is 6 hours, and the ocean model is at 24 hours time interval. So the model training here shows that we use a spherical Fourier neural operator. So here is the hyperparameter we are training for the atmospheric model and the ocean model. There are two. The difference between these two models is that for the model complexity, the embedded dimension and the operator layers. So on here we show some preliminary results on the top right. So because we only show the 2-meter temperature, the surface for the surface variable, and the 500 pressure layer for the geopotential height. So this shows on the left column shows on the northern hemisphere, and in the middle shows the southern hemisphere, and on the right shows the tropics. As you can see here, so over 1 year simulation, the model is stable. and we see the seasonal, the annual cycle also can be reproduced, but we still see some that the worst over the summertime, we see the under predicted 2 meter temperature and the geopotential height. So on the left, bottom left, it shows the sea surface temperature from the ocean model. So here, from the top one shows the 1 month simulation, and the bottom shows the 6 months.
Yeah. Sorry to cut you off, but we are at 3 minutes. So if you could wrap it up, please.
Yeah. So here we show the feasibility of to develop a coupled atmospheric and ocean model for the subseasonal to seasonal forecasting. So it shows the promising results. I would like to answer your question if you are interested. Yeah. Thank you.
And it looks like we have our second presenter on.
Hi, thank you so much for the opportunity. Let me share my screen. Okay. Can you see my screen?
Yes, we can see it.
Perfect, thank you. So, hello everyone, I'm Atiya Alipur. Today I'm presenting Neurocast, a neural operator-based model for bias correction in forecast guidance. I'm presenting this work on behalf of my colleagues in the Office of Coast Survey at NOAA's National Ocean Service, as well as our collaborator at NVIDIA. So the challenge we are addressing here is that numerical models often use inputs that are biased and contains error, which can affect their accuracy. Also, no matter how sophisticated numerical models are, they are always a simplification of physical processes in the model setup. So to address this, we developed Neurocast to correct these biases. We applied Neurocast to NOAA's staff's 2D global water level forecast guidance. And here in figure 3, you can see the workflow of Neurocast that we have used for this. So the advantage of Neurocast compared to other deep learning model is that it can map between function spaces. So this allows us to learn the model biases at a limited number of points, and then we can use that map to predict bias at other location where we do not have observation. To test this workflow, we focused on the Northeast United States. We selected 17 stations to train the model on the data from 2021 to 2023, and we tested the model on the data of the 2024 at those 17 stations, as well as some other stations that we didn't use during the training. So as you can see in figure 4, the result shows that using different performance metrics, the model performance after bias correction significantly improved, and the bias was reduced by over 80%. Looking at the box plots in figure 5, we can see that the bias reduction was consistent across all the lead times. And in addition to those evaluation, to evaluate the model's performance under both general and extreme weather condition, we separated some extreme events from the analysis. And as you can see in figure 6, the model performance after bias correction improved during both a general and extreme weather condition. So definitely there are a lot of details that we can explain, but yeah, that's for this poster presentation. Yeah, so please feel free to contact us if you have any question. Thank you very much.
And it looks like we have Barry Baker back. Great, we see your presentation. If you can just unmute. Thank you.
There you go. Okay, so good morning, good afternoon. I'm trying this again. This is introducing the global chemistry and aerosol forecast system, or GCAS version 1. This will be replacing the current operational model of GEPS aerosol. GCAPS is a UFS-based system designed to provide critical global analysis and forecasts for a wide range of aerosols, including dust, sea salt, sulfate, and black carbon. These forecasts are vital for numerous applications, from predicting UV levels and estimating surface particulate matter to forecasting major events like dust storms and wildfire smoke. GCAPS serves as a foundational system by providing lateral boundary conditions for regional models, particularly for the UFS AQM or National Air Quality Forecast capability, and it lays the groundwork for even more comprehensive aerosol and trace gas operational forecast systems in the future. The system is designed for atmospheric composition forecast operating at C384, which is approximately 25 kilometers with 127 vertical layers. At its core, GCAPS version 1 integrates the NASA GoCart 2G model as an inline component within the UFS. GoCart 2G is a bulk aerosol model where the dust emissions are described by the NOAA-developed FUNCSA emission scheme and a unique large-scale wet deposition that was originally from the GeoSchem model. A crucial development in GCAPS version 1 is enabling radiative feedback in the physics scheme, which allows prognostic aerosols to directly influence the meteorological predictions. Furthermore, anthropogenic emissions in GCAPS are handled by the NOAA Emission and Exchange Unified System, or NEXUS, which utilizes global monthly emission data sets and applies diurnal profiles. The system itself comprises of two main components: the GCAPS free forecast, which generates our gridded aerosol products, as well as the Global Constituent Data Assimilation System, or GCDAS. The aerosol analysis within GCDAS is performed using the Joint Effort for Data Assimilation Integration, or JEDI framework, which this is a major milestone, being the first implementation of JEDI within the National Weather Service operations, assimilating VIIR's AOD products from NESDIS. Looking ahead, GCAPS version 1 represents a significant step forward, but this isn't the end. The main advancements for GCAPS version 1 include the direct feedback and replacement for GEPS aerosol, utilizing the latest model code and parameterizations, and crucially, the implementation of aerosol data assimilation to constrain our forecasts. In the near future, we envision version 2 of GCAPS incorporating even more
Barry,
advanced features.
Sorry to cut you off, but you are at your time.
No worries. Thank you.
We have Chen back.
Does my screen looks all right?
Yes, if you can go full screen.
Yep.
It looks great.
Is it first? Okay. Hi, everyone. Chi Hong here from University of Oklahoma. So usually for a AI global weather forecast model, we care about how much RMSE is reduced. We care about how long the predictability has been extended, and we care about how well the cyclone track intensity is predicted. But in the ensemble data simulation field, what we care most is the background ensemble covariance in short-term forecast. So the research question is simple. Can AI model get the 6-hour background ensemble covariance right for tropical cyclones? We compare 6-hour forecast of a GraphCast ensemble against the GEFS ensemble during two phases of Hurricane Lee 2023, a non-rapid intensification phase and a rapid intensification phase. We look at three aspects: the TC vortex, the TC environment, and the interaction between the two. So for the TC vortex, first, we find out GraphCast ensemble spread is much smaller, especially during the rapid intensification phase. We also find GraphCast handle univariable correlation better than cross-variable correlation. Moreover, we find the secondary circulation and outflow deposit are weaker in the GraphCast, and the variability of a primary circulation is also of different structure compared to GEFS. In the broader environment, using PCA, we find GraphCast is not only under-dispersive, but also more noisy. Looking at different variables, we found there are certain biases that only exist in the geopotential height field. GraphCast tends to underestimate the correlation in geoptimal height and tends to create more noise. This tells us geoptimal height may need some special attention if you ever want to use GraphCast ensemble in data simulation. For the vortex and environment interaction, we find that during the rapid intensification phase, GraphCast failed to capture the correlation between the cyclone intensity and large-scale features. But for cyclone tracks, GraphCast produce the matching correlation pattern. Some takeaway points. GraphCast ensemble is under-dispersed, so inflation may be needed if we want to use it in DA. And GraphCast may not doing great on certain physics aspects, for example, the secondary circulation of TC and the integration to calculate geoptimal height, and also distant correlation between the TC and other features. Thank you. I'm happy to answer any questions.
All right, thank you. And next is Faribor's Dineshvar with evaluating the effect of wave and hydrology coupling on tropical cyclone-driven storm surge.
Hello, Hi, can you hear me?
Yes.
And I shared my presentation. If you confirm that you can see that, so you can go ahead.
Yep, looks good.
Great, thank you. Hi, everyone. I'm Fariborz Daneshvar from the Office of Coast Survey at NOAA National Ocean Service and will present the effect of wave and hydrology coupling on tropical cyclone-driven storm surge. Forcing factors such as wave and hydrology have nonlinear impacts on water level and cannot be simply aggregated on top of each other. Instead, a comprehensive analysis would be needed to provide a more accurate evaluation of water level. Here I'll be looking into two major storms from 2024 Atlantic hurricane season to quantify the effect of hydrology and wave on storm surge. Hurricane Helene was a Category 4 storm that made landfall in late September in Big Bend, and Hurricane Milton was a Category 5 storm that made landfall as a Category 3 on the West Coast on early October. Both of these two storms caused a significant number of fatalities and damage to the US. I used Schism for hydrodynamic modeling and OCS mesh to develop a subset from the high-resolution Stubbs mesh in the region of interest and coarse mesh elsewhere. I used TPXO dataset for tidal forcing and generalized asymmetric Holland model or GAM for atmospheric forcing. I used National Water Model as source sink input to the Schism model and third-generation wind wave model or WWM for wave coupling. Comparison of simulated maximum water elevations and observations at USGS sensors showed that the fully coupled model with inland hydrology and wave provides a better prediction of the high peaks. On the right, you will see the isolated effect of inland hydrology and wave coupling for Helene and Milton in big picture and also two zoomed regions. As you see, in some locations, the inland hydrology and wave coupling will result in up to 0.5 meter higher water elevations, which would be significant if we ignore that. And this analysis signify the importance of inland hydrology and wave coupling for more accurate prediction of storm surge. Yep, that's all.
Thank you. And next will be Oliver Elbert, Keeping Pace, Unlocking AI in Exascale with Domain-Specific Languages.
I don't see that person online, so we can move on to the next.
All right, next will be David Harrison, Assessing the Skill and Sensitivity of AI-Generated Global NWP Emulators in the NOAA HWT Spring Forecasting Experiment.
All right, hello everyone. Can you see my screen and does my mic sound all right?
Yes and yes.
All right, awesome. So we have recently seen a rapid exploration and development of artificial intelligence, specifically for global weather prediction in both the private and government sectors. These machine learning-based models are designed to emulate the more traditional numerical weather prediction models that we have, such as the GFS or the ECMWF. But these machine learning models have been shown to provide a similar skill to the traditional NWP, but while using fewer computational resources. However, these systems have so far only received a limited amount of evaluation within real-time operational settings. To address this need, we tested 5 state-of-the-art AI-based NWP emulators during the 2025 spring forecasting experiment, with the goal to assess what utility these models provide for severe weather forecasting, especially at longer lead times, and to assess if different initial conditions impact the performance of these emulators. So during the experiment, participants evaluated these emulators at 7-day lead times and assessed their forecasts of 500 and 850 millibar height and wind fields, as well as 2-meter temperature and 6-hour QPF. These emulators were initialized using either the GFS initial conditions or the ECMWF initial conditions, and those forecasts were then compared to the respective GFS or ECMWF analysis. We also included one direct comparison of Google's GraphCast model, initialized using both GFS and ECMWF initial conditions. This gave us a direct one-on-one comparison between those two different initial condition sets. Model names were hidden during the evaluation, so participants were unable to determine which forecast came from which model, and the operational GFS and ECMWF were also provided as control models for us to compare against after the fact. So looking at the results, overall, most of the AI-based NWP emulators were given similar or slightly higher ratings than the operational models. Pengu Weather overall received the highest mean score of the models initialized using GFS initial conditions, while the AIFS received the highest ratings of the models with ECMWF initial conditions. Microsoft's Aurora model was found to produce much smoother forecasts than the other models overall, and was generally rated the lowest on average. Participants overall gave the models with the ECMWF initial conditions slightly higher ratings on average than those with GFS initial conditions, and they specifically noted that the models with the ECMWF initial conditions tended to provide sharper features and more realistic depictions of jets within the wind field. So overall, the AI-based NWP emulators have shown great potential for operational applications, although participants did note that additional model levels, fields, and derived parameters will be needed in the long run before these forecasts are particularly useful. And that's all I have.
Alrighty, thank you. And next will be Arian Haruni with
Yes, that is.
Agentic LLM Framework for Fast Interpretable Data Queries, Application to STOFs.
Mm-hmm. Let me share my screen. Can you view the screen right now?
Yes.
Okay, perfect. So we have developed a framework, a multi-agent framework for data retrieval and analysis using LLMs, particularly tool calling LLMs and some LangChain frameworks. So right now the framework has 3 agents: an orchestrator, an analyst, and a data retrieval agent. The user talks only to the orchestrator, and the orchestrator parses the user's queries and inputs and delegates tasks to the retrieval agent or the analyst agent. This allows for complex queries or multi-step queries to be interpreted by the orchestrator and executed by each agent. The retrieval agent is the more simpler agent. It has tools for raw data, post-processed data, and even documents through stuffs that you can access and read. And if the retrieval agent calls any tools, the results of those tool calls go exactly to the orchestrator again, and the orchestrator generates a answer that the user can read. This allows for non-expert users and expert users to access SOFS data and interpret those data in a useful manner for their tasks. The analyst agent is the more complex of those. It can either produce outputs directly or delegate information to the orchestrator and continue with more complex queries. the analyst can visualize, interpret, and do statistical evaluations on the data that is retrieved by the retrieval agent. This allows for faster, more efficient, and less technical data retrieval and interpretation for expert developers and non-expert users throughout different models and different data sets. Here's a sample chat that you can see. There is queries, natural language queries that will be parsed by the orchestrator. The orchestrator either calls the analyst or calls the data retrieval agent, which either of them can choose whether to call a tool or ask the orchestrator for a better prompt, a more specific prompt. This is a very applicable framework. We can add more agents or use
Aaron,
bigger models.
I'm gonna have to cut you off there. Thank you.
Oh, thank you.
All right, and next will be Manzur Ali Jassan with a containerized WCOS2 environment for collaborative development of operational ocean forecast systems.
Can you see my screen?
Yes.
Okay. Hi everyone, my name is Mansoor Ali Jisan from NOAA Co-ops, and today I'm going to present our work on creating a containerized WCOS2 environment in support of operational ocean forecast system development. As many of you know, that operational ocean forecast system that NOAA runs, they operates on the weather and climate operational supercomputing system. Due to accessibility and package restrictions, external collaborators cannot directly use the WCOS2 environment, and this creates a bottleneck in research to operation transitions. To address this issue, we developed a containerized environment closely emulating the WCOS2's production environment. So in the diagram that I'm showing here, in the middle column, you can see the architecture of the container. We use Docker as the software for developing this container. The container includes ECFlow as the workflow server. It also includes Slurm job scheduler as well as the MySQL as database manager. Inside the container, we have the NCEP software stack, for example, libbasio, bufferlib, IP, etc. We build those NCEP software stack from their respective GitHub repo during the container build process. The critical part of the container is these two hydrodynamic models, Schism and EDSERP, which are the hydrodynamic engine of NOAA's Storm Surge Tide operational forecast system. We compile these two hydrodynamic models inside the container from their respective GitHub repo during this container build process. We use the exact same version of this software that we use in the operation inside the container. To mount the necessary input data into the container and to emulate the NCO's data hierarchy, we use Docker's volume mapping to map the data from the local host, which in this case is NOAA's parallel work, into the container environment. As you know, that container has very limited storage, so we cannot just copy that file into the container environment. So when we map the data from the host machine to the container, we follow the same data hierarchy that we use in the WCOS2 production environment. So this container setup allows us to execute the end-to-end workflow of the Storm Surge Tide operational workflow for the Atlantic system. So covering the nowcast forecast, pre-processing, nowcast forecast, and post-processing without modifying the operational job script. So in short, this container feels, looks, and runs like the WCOS2 production environment, but it can be deployed anywhere in HPC, cloud,
Mansoor,
or in local system. Yep.
I'm gonna have to cut you off there. Thank you.
Right, thank you.
All right, and then next is Yushin Kim with impact of assimilating atmospheric boundary layer observations on the rapid intensification of Hurricane Idalia 2023 and self-cycled HAFS JEDI system.
Okay, can you see my screen now?
Yes.
Yes, this distribution came from the University of Ghana, and I'm presenting the impact of assimilating atmospheric boundary layer observations, which could capture the LC interaction during the rapid intensification of Hurricane Idalia. So currently we are using Hurricane Analysis and Forecast System HAFS and JEDI framework. So using this system, actually, we are conducting two experiments. The first one is estimating all observations, including the drop zones data, which could capture the atmospheric boundary layer during the hurricane core. And also, we conducted data denial experiment, which is no ABR experiment, which excludes the drop zones data within the atmospheric boundary layer. So during our data assimilation period, actually the ABA temperature is generally underestimated compared to the assimilated drop zones data. And so assimilating such drop zones data reduces the overall positive or minus B error throughout the DA cycling, which is the pink lines. So by the end of the DA cycle, being on the right figure, our observation experiment analyzes a warmer atmospheric boundary layer temperature near the hurricane core compared to no ABR experiment. So these changes in the atmospheric boundary layer leads to the changes in hurricane structure. So on the left panel, our observation analyzes higher ABR temperature compared to no ABR experiment, which is leading to the warmer hurricane core at mid levels and enhanced low-level inflow toward the hurricane spur. So in the 24-hour forecast on the right panel, our observation stimulates stronger tangential and radial wind around the hurricane spur, also maintains higher atmospheric boundary layer temperature, potentially through the LC interaction during our copper projection system. So in our verification for the intensity, so the all observation experiment more accurately reproduced the observed peak intensity as Kepler hurricane, but the no-ABR experiment could produce just Cat2 hurricane. So such improvement in hurricane intensity correspond to more organized hurricanes core structure with in wind and the hydrometeor field. So let's recap. So this study underscores the impact of assimilating atmospheric boundary layer, which could capture the LC interaction. So assimilating such information leads to the improved forecast of the hurricane's rapid intensification, but we'd like to explicitly account for such LC interaction in our DA system. So Heather will further develop and evaluate strongly or weakly coupled DA system within self-cycled HAFS and JEDI framework. Thank you for your attention.
All right, thank you. And next will be Connor Llewellyn with generative data simulation of weather observations for high-resolution CONUS-wide weather state estimation.
Thank you. Can you guys see my screen okay?
No, we cannot.
Looks like he's frozen. We can move on to the next, and I will keep an eye on Connor.
All right, next will be...
We see you now.
Never mind. We can see your presentation now.
Can you guys hear me okay? Sorry about that.
Yes,
Yep,
please.
you're good to go.
Please.
Okay, thanks. Connor Llewellyn with the MITRE Corporation. I want to present on some work with NVIDIA and TempoQuest looking at generative data simulation for high-resolution CONUS-wide weather state estimation. This is really looking at new methods for data assimilation to try to make that typically computationally intensive process for numerical weather prediction a little more efficient using generative data assimilation. This work builds on previous approaches using diffusion-based frameworks conducted previously. The differences here are using a higher resolution data set, a 1 kilometer CONUS-wide data set, and a novel data assimilation framework. So a little more on that training data set. Project team worked with a company called TempoQuest, who has a GPU accelerated version of WRF AceCast to develop a 1 kilometer spatial resolution 10-minute temporal resolution 2-year data set to train the generative model. This is a picture in the bottom left here. It was going to be an animated GIF, but I chickened out at the last minute. I'm glad I did because I think this would have totally crashed on me. This is comparing the 1 hour time step of the HER compared to the 10-minute time step of the AceCast simulation, and 3 kilometer versus 1 kilometer. So higher resolution, both spatially and temporally, for a storm in southern Florida. The generative data assimilation approach we use has been previously written about and evaluated in previous work by Manshausen and Rosé and Lupe. The differences here is we're taking what was a regional approach and expanding it to a nationwide approach in the continental United States, and training it at a higher resolution, 3 kilometer versus 1 kilometer. This shows what the initial diffusion model training looks like. It really starts with a static image, and there's a denoiser operator that's trained to remove that noise and recreate the physics of the physics-based model. You can see what some of those outputs look like in the bottom images here. So the left is the physics-based model output. The right is the unconditioned, non-data assimilated model output from the generative AI model. So you can see physical structures for temperature are fairly well accounted for there. Next, we use the NOAA Integrated Surface Database to assimilate weather station data, surface level weather station data at this point, to make that forecast more accurate. We did a 80-20 train test split for areas of interest throughout the continental United States. This is showing some results for California, specifically for temperature and 10-meter winds. And we were seeing that the results of this model actually capture the physics fairly well. In some cases more accurate for winds, less accurate for temperature. So red here is the WRF physics-based model, blue is the generative AI data simulation model. So encouraging results there. Future research, we're continuing evaluation of this, expanding this to include three-dimensional figures and guidance. Yes, thank you very much. Happy to answer your questions.
Thank you. Next will be Siki Lee, development of a coupled FVCOM NWM model for ocean hydrology interaction.
Can everyone see my screen?
Yes.
Thank you. Hi everyone. My name is Siki Lee. I work in University of Massachusetts Dartmouth as an assistant research professor. So our topic would be the development of coupled FVCOM national water model for ocean hydrology interaction. So we have developed a coupled model between our ocean model FVCOM and the national water model. So the reason we did this coupling work is due to achieving the simulation of the compound flooding in the coastal area. So we know that during the summer and autumn season, some coastal regions are under flooding, potential flooding due to the precipitation, the upstream river discharge, the storm surge, and the wave runoff. In order to do the true simulation for the compound flooding, so we achieved the coupling model. So due to the limited time, I will show 3 features of our coupled model. The first one is about the coupled model framework. So in our model, we achieved the data transfer from the national water model to FVCOM in the online method. So in detail, national water model will provide river velocity and discharge to the ocean part, so that the ocean model can get a more accurate and frequent river forcing from the true river model. And for the grid, because FVCOM is in unstructured 3D grid and the national water model is in the 1D route link, so we developed a new method to do the coupling between these 2 different maps. And the second feature is that now we developed a new method to input the forcing from the river model called the route-informed discharge injection. So traditionally, model will usually put the river discharge on one point, but in our new method, we divided the river discharge into different parts and put into the ocean model in several different places so that to increase the stability. So the third feature will be we include the machine learning method for the river temperature, and we set a PNN method and train the data for 4 years, and using the current trained model, we got some interesting results, and the prediction result is really good. So that's all for me. Thank you.
All right, thank you. And next is Jianjun Liu, improving GFS surface fields using a deep learning bias correction model.
So can you see my screen?
Yes.
Okay, thank you. Hello everyone. Today I'm going to present our work that is improving GFS surface field using a deep learning bias correction model. This study focused on addressing systematic errors in the GFS through the machine learning. Numerical weather forecast models such as the GFS produce in situ forecast. However, they still exhibit systemic bias. To decrease the bias, we developed a deep learning-based bias correction model. Initially, the method was applied to reduce bias in operational GFS 2-meter temperature over convex domain with promising results. This study extends the framework both in scope to multiple surface variables and in scale to the global domain. And we developed variable-specific unit models with the convolutional block attention modules to improve future representation. As indicated in Figure 1, the models target several GFS variables, including 2-meter temperature and dew point temperature, maximum minimum temperature, and 10-meter wind components, speeding, and direction. Training uses ER5 for the temperature and wind variables and GDAS for maximum and minimal temperatures. We primarily trained at a single forecast hour, but at other leading times were used if necessary. The evaluation metrics including the bias, mean absolute error, mean square error, and scale score. Evaluation results showed the significant improvements in the forecast scales at 22 hours. Forecasting as an example, the model in fact reduced both positive and negative bias. And for the scale, as measured in terms of RMSE, the model significantly decreased the annual and seasonal mean RMSE over the global domain, and also the annual mean RMSE across climate regions. For the tropicals to the polar zones, importantly, despite being trained on the limited leading time, the model generalized effectively across all forecasting leading time with consistent improvements in both RMSE and bias. So to conclude, we demonstrate that our developed model significantly improves GFS surface forecast globally with robust performance across variables, leading time, and regional. This demonstrates strong potential for operational application and also further extension to other forecast systems. If you want to see the more detail about model structure, setting, and performance, you can see the reference, and also the code can be accessed from the repository. So any comments or questions are welcome, and thank you for your participation. That's all.
All right, thank you. And next is Haibo Xu, storm surge and coastal inundation, nowcast forecast during Hurricane Helene and Milton.
So my screen is good? Hello?
Yes, we can see it now.
Oh, okay, good. So hello everyone, my name is Haibo Su, postdoc from USF. Today I'm going to give a short talk about the storm surge and the inundation nowcast forecast during Helene and Milton. As you all
Haibo,
know,
can you full screen your poster?
Oh, yeah. Better? Okay. So as you all know, the last year's the Florida west coast hit by two hurricanes really bad, and in that case, we use AFRICOM models based WFCOM, TBCOM, and the EFCOM models together to get the nowcast and the forecast informations during the hurricane seasons. So this model, we run the models 5 days in a row, and during the hurricanes, Helene and Milton's, and you can see the figures. The results compared with compare against with observations is get better and better. And for the 1 days behind the landfalls and the performance, the forecasting performance is really good. And also, so we develop inundations models, which we extend the mesh grid from bay on land. So basically, the waters can get inland and offshore and on inshores for sure. So from these figures, you can see that is like high level marks happened for Helene. A lot of inundations, really severe inundations, can be observed. And when we compare the models inundations with high water marks provided by FEMA, and we created these figures, the mean errors is about 0.5 feet. So I'm here to answer any questions if you have. Thank you.
All right, thank you. And next will be Thiru Vengatam Padmanabhan, improving background error covariance and square root estimation with the convolution neural network in the gain form ensemble transform Kalman filter.
Hi, can you see my screen?
Yes.
Hello everyone, I am Thiruvengadam. I am presenting our work on improving background error covariance in the GETKF system using the convolutional neural network. The motivation behind our study is in ensemble data assimilation, the accuracy of background error covariance is often limited by the sampling errors, especially when using small ensemble members. Traditional ensemble expansion methods like the GC approach help, but have limitations. They can't correct the variance errors, require additional inflation, and lack adaptiveness. It also demands a higher computational cost in representing small-scale features. So to address this, we propose using CNNs to generate extended ensemble members. We tested the CNN expansion at different spatial scales and compared it to the GC approach. We evaluated the method in 2 scenarios. An equal cost scenario where CNN and GC use the same number of expanded ensembles to compare accuracy, and a reduced cost scenario where the CNN used far fewer members to test the computational efficiency of the CNN. So our results show that at equal computational cost, CNN achieves a lower covariance RMSE than the GC, with the improvements due to better variance and the correlation. Our reduced cost experiment showed that CNN-based ensemble expansion was able to maintain a better covariance while using over 85% fewer expanded members, making it a cost-effective solution. When using these expanded members within a GETKF system, we observed that the CNN consistently reduced analysis RMSE and improved ensemble reliability both at equal and the reduced cost scenario. In summary, like the CNN-based ensemble expansion proposed method outperforms the traditional GC method by correcting both variance and the correlation errors. It delivers better accuracy and ensemble reliability, even with the significantly fewer ensemble members, making it a computationally efficient solution. Thank you for your attention.
Thank you. And next is Lee Pan, application of aerosol budget analysis method to 2 generations of NOAA global aerosol forecast models.
Can you see my screen?
We can, if you could just go into presentation mode.
Okay, my name is Li Pan from NOAA EMC. Today I want to talk to the application aerosol budget analysis method on the
Lee,
Yes.
Could you full screen your presentation?
Yes, I did. Can I keep going?
You might not be sharing the correct screen or slide deck.
Let me
Try
again.
resharing. Yeah.
Sorry. Is that good?
Yes.
Yeah, thank you. So I'm Liban from NOAA EMC. Today I will present the application Aerosol budget analysis method on the two generation NOAA global aerosol forecast models. So what is two generation NOAA global forecast model? So NOAA will retire the current operation GFS aerosol model in 2026 with the replace of the GCAPS. GCAPS is a global chemistry and aerosol forecast system. So that requires the GCAPS, the new model should outperform than the old one, the GF aerosol. But it's not an easy task because the GCAPS model is a chemical component of UIFS. UIFS is a unified forecasting system. It's a framework of the modeling Earth system, also include other components like atmosphere, ocean, and waves. So the GCAP is a very complex model system. Usually when we do the model simulation, it will result not as we expect. We tune the model, we call the model sensitivity study, but for this case, since the GCAP is a very complex system, it's increasingly difficult to do that because we usually get the similar good result and bad result at the same time. So in case of this, we need some method to help. So this method is called the aerosol budget analysis. So before discussing the aerosol budget analysis, I will want to give example. This example is CSOL AOD monthly simulated by the Merchu and the GFS also for October 2019. In this example, you will see the different input for the model to the different model will automatically generate the similar result. So if you see the AOD is very similar, but if you look at the seesaw, the emissions, dry deposition, wide deposition, and also sedimentation, you see the how difference. So from this example, we learned that the intermediate process, like for aerosols, the chemical and the physical process, is how important for the aerosol simulations. So what is a budget analysis for aerosol? So aerosol budget analysis is dependent on the aerosol mass conservation law. For each aerosol species in the model simulation domain. So the budget analysis can be expressed as the mass balance equation. Yes.
Sorry, we're gonna have to cut you off. Your time is up. Thank you.
Okay, thank you.
Next is Benjamin Rustin, Jedi Skylab Observation, Assessment, and Evaluation.
All right, you can hear me okay? My name, I'm assuming yes.
Yes.
But my name is Ben Rustin. I'm on the OBS team at the Joint Center for Satellite Data Assimilation. And I'll turn off my hidey hole. I'm actually going to just run through this poster really quickly. There's many collaborators on this from the team. The JEDI project, which has been mentioned a few times already, is an abstracted framework to allow you to do data assimilation for a number of domains. I am now published in space weather. We are using this in ionosphere. It's used in ocean. It's used in land. It's used in atmosphere. And it's also used by private industry. It's operational at the Weather Service or Weather Company, as well as NOAA, NASA. The Met Office is going to go operational with this at the end of the year. Our partners are Air Force, Offutt. I've been to Offutt a number of times and worked with the 16th Weather Squadron there and their commercial data evaluation team. So the idea is really to do an agile framework so people don't go off, develop something for 6 months, and then show up with this giant pull request that then we have to iterate with them and get it back in line. We want to do things in a quick time scale. Here's an example of JEDI being used with the GFS version 17 atmospheric model for an international experiment led by a CGMS working group. This is the base is what operational centers have in real time for radio occultation, and then we've supplemented. The Romex 20K is really close to what we're going to have through commercial acquisitions here shortly. But Romex, we had 5 times the operational volumes, and you see as you increase the number of GNSSRO, the scores in T and Q as referenced by Radioson. So the different experiments your Radioson fits are getting better and better. We have a publication on that, but those results are consistent with our partners in the experiment, ECMWF, Deutsche Wetterdienst, Meteo France, the Met Office. NOAA isn't allowed to use foreign data, so they kind of participate. It's a long story. Commercial data pilots, Air Force has one, NOAA NESDIS has one. We collaborate with them on those. We also have evaluation tools. We use MetPlus, WeatherBench X, which is from Google. These are results from WeatherBench X scorecard we have. This is for the NOAA NESDIS pilot for ocean surface wind. These are GNSS reflectometry. The transmitter bounces off the surface. You collect that and you have some information on wind speed. These are just time series of the results from above. And then last, very hot, also in the arena is now microwave sounders. Tropics is a NASA mission, and then the Tomorrow microwave sounder is built off Tropics. There's a preprint of a paper from the Tomorrow folks. The Tropics folks, Vince Leslie and Bill Blackwell, are also on this publication. But if you need more details on the Tomorrow, they have 7 satellites in orbit. They're about to launch 3 more. Here's some data that I got through the Air Force pilot, and I was evaluating just the fits, the blue before bias correction, the red after bias correction, and just for 2 of the channels, water vapor channel and a sounding channel. And then again, the resulting fits to
Benjamin,
Radioson. I'll finish here in 10 seconds.
All right.
So just the blue line is a better fit when you add the Tomorrow IO data from a very deprecated system. But look us up, and thank you for your time.
Thank you. And next is Rohit Shukla, harnessing machine learning and explainable AI to predict phytoplankton blooms and identify key drivers in freshwater reservoirs.
Am I audible?
Yes, you're a little quiet.
Okay. Is it better now?
That's better.
Okay, thank you. So good afternoon, everyone. Today I'm going to talk about my ongoing work, which is the application of machine learning to identify the key drivers, as also have multi-step forecasting. Basically, my motivation is to understand how a harmful algal bloom has been threat to ecology and operation and to human health. And traditionally process-based model has been shown that they have parameter uncertainty. They are computationally and operationally expensive. So considering those challenges, we have tried to implement machine learning-based forecasting as well as time series-based explainable AI for effective water quality management. So basically, this is my workflow. In a nutshell, this workflow is basically implementing explainable AI for better model interpretability. Then we have implemented defined by run API-based multi-objective hyperparameter tuning to create an automated system for real-time optimization. Then we have tried to implement multi-step chlorophyll air forecasting and feature importance across different forecast horizons. Then for uncertainty, we have implemented bootstrap-based ensemble machine learning models. So if you would see this graph, we have currently implemented on 2 drinking water reservoirs in Western Virginia. We are hoping to get it in some other reservoirs. Basically, these 2 reservoirs, we have real-time water quality updated in a cloud-based system. That's why we have been able to implement machine learning-based forecasting on these 2 reservoirs, but we would definitely be implementing on some other reservoirs in like very soon. So our explainable AI results basically shows that the even though these two reservoirs very closely co-located, but they had different drivers. Falling Creek Reservoir had bottom water oxygen and dissolved organic matter as the important drivers, whereas the Beaver Dam Reservoir had seasonality and dissolved organic matter as one of the drivers. Like across different machine learning algorithms, we found that XGBoost model was our best performing model across two reservoirs. And the good finding was that even at the 7-day forecast horizon, our model was able to get like very reasonable forecasting capability, which was around 90% accuracy. Based on that, we also implemented our forecast, like 7-day forecast horizon feature importance. Basically, this analysis was done for the Virginia Authority Management to understand what are the drivers important for 7-day chlorophyll A. And we found that for initial day 1 to 3, that initial chlorophyll A was the forecast, like important driver, which basically showed that it was a persistent of chlorophyll A. Then we found that across 4 to 7 days horizon, that environmental variables, that water temperature and organic matter were steadily increasing with importance, which was good for the authority people to understand and make informed decisions. Then we implemented bootstrap-based ensemble model to understand the forecasting skill, and we found out that the ensemble model up to 50 members were
Rohit,
reasonably well.
I'm gonna have to cut you off. Thank you.
Okay, thank you.
Next is Jacob Steinberg toward improved forecast of U.S. East Coast sea level development of a dynamical downscaling framework to simulate North Atlantic circulation and physically informed sub-annual forecast skill.
Thank you. I am just sharing my screen. Can you see that?
Looks good.
Okay, great. Thank you so much for having me. My name is Jake Steinberg. I am a research scientist at NOAA's Geophysical Fluid Dynamics Laboratory. And today I wanted to share a little bit of work that highlights the development and use of a dynamical downscaling framework to assess U.S. East Coast sea level predictability, really forecast skill. So the models we're using is the SPEAR, Seamless System for Prediction and Earth System Research for Global Modeling System. It's a 1-degree ocean model, and we're downscaling that with a 1/12 of a degree regional simulation in the Northwest Atlantic. This regional model is 1/12 of a degree, and we build a 400-member ensemble of 1-year retrospective forecasts to assess daily to monthly variability, particularly along the U.S. East coasts. And so the panels in the lower left here just show the mean and variability states of an observational product, the parent 1-degree model, and our 1/12 of a degree regional ocean model. The right half of this poster shows the analysis kind of pipeline framework that we've taken. We extract sea level at coastal tide gauge stations along the U.S. East Coast. We do some pre-processing to get daily time series, and that facilitates comparison of our regional model, this 1/12 degree model, to our parent 1-degree model and observations. So the interesting results that I wanted to share are when we look at the frequency distributions or energy as a function of frequency along the U.S. East Coast in these 3 different products. Again, the observations, the SPEAR 1-degree model, and then our downscaled model. So this middle panel with the black and purples shows in the 5-day to 2-week band where we see an increase of variance. The left panel is SPEAR, the middle panel is NWA12, the right panel is that difference. And so everywhere you see red, we're seeing an enhancement of variance and energy in this frequency band. The next row down shows, as a function of all frequencies that we considered from months to days, how the dynamical downscaling improves our simulation of sea level, but it really depends on where you are. Particularly south of Cape Cod, south of Cape Hatteras, we really see a lot of improvement or enhanced variability. And we also look at daily distributions of sea level as a function of lead time. to consider extremes and when they occur over the course of the year. And we really see improvement again in the southern, along the southern coastlines. I think I have a few seconds left, and I'll just say thanks very much. Please send me an email if you'd like to follow up or have questions. Thank you.
All right, thank you. And next is Eunice Tabahi, Advancing Forecasting Capabilities of Dust and Health Impact through the Saharan Oscillation Index and Machine Learning.
I don't see that person in the call. We can move on to the next.
All right, next presenter is Lixia Wang, the evaluation of a data assimilative Northeast Coastal Operational Forecast System in 2021.
Lixia, you can start sharing your screen. You are muted at the moment. You can just click that little, okay. You can click the little pop-up that says unmute on top.
How about now?
We can hear you.
Yeah, I'm trying to share my screen. Can you see my screen?
We can see your slide, yes. You can go full screen and, yep.
Okay. Hello, everyone. My name is Lixia.
All right.
Nico.
Lixia, we're having some issues with audio. Let's work together offline and we'll come back to you.
Okay.
Yeah, we can probably move on to the next. Okay.
All right, next is Yangming Wang, Generating Cost Savings Surrogate Background Ensemble with GNN-based Mapcast for estimating multiscale background error covariances.
Okay, can you see my screen?
Yes.
Okay, great. Hello, everyone. My name is Yuming Wang from the University of Oklahoma. I first would like to acknowledge my co-author, Professor Xiguang Wang. Today, we would like to introduce our recent work about the machine learning-based emulator Mapcast for estimating multi-scale background error covariance within ensemble-based data assimilation. Generating an ensemble background can be computationally expensive, especially for the convention allowing ensembles. As the success of prior machine learning emulators to generate forecasts cost effectively, but limited studies on the background error covariance estimation. This study focused on the developing and evaluating the machine learning emulator to generate surrogate background ensemble for convection, allowing multi-scale ensemble-based data assimilation. For this purpose, we generated the training data sets using MPath model initialized from the rep analysis with a 15 minutes time step and a 3 kilometer grid spacing. These are the included variables, include the 3D and 2D variables. And here, this figure shows the Mapcast architecture. Here are the results from this emulator. Evaluation of a single ensemble members shows Mapcast and MPath model obtained similar code pool and composite reflectivity distributions as well as the data distributions. Regarding the spectral distributions, Mapcast basically replicates MPAS model forecasts except for the donor wind and the temperature at the small scales. The two models also have the similar ensemble means for the composite reflectivity and the temperature. They also have the similar ensemble spread, except for the reflectivity. Next, we will evaluate the multi-scale ensemble correlation. MapCast emulates MPAS spatial correlation well, especially when MPAS correlation shows large values compared to the full-scale correlation. MapCast performs better at decomposing the large and small scales. The same conclusion can be applied for the reflectivity. In terms of the cross-variable correlation, MapCast and MPAS have larger difference in the cross-variable correlation compared to the same variable correlation. In summary, a machine learning-based emulator aiming for multi-scale DA and prediction is developed. And for this surrogate background ensemble evaluation...
Okay. I'm going to have to cut you off. Your time is up.
Okay.
Thank you.
Thank you.
If we can try going back to Wixia. Wixia, please go ahead and share.
Okay. I'm trying to share my screen right now. Can you see it now?
Yes,
Hello?
we see it.
Okay. Yeah. Okay, sorry. Yeah. I'm going to present the evaluation of a data simulated Northeast Coast operational forecast system, which calls NICOPS, from a 6 months handcast simulation, July 21st to December 31, 2021. NOAA, National Ocean Service, has been jointly developing and testing this new NICOP and will operationally implement it on NOAA's weather and climate operational supercomputing system by the end of fiscal year 27 Q1. This new NICOPS combined the optimal interpolation and the nudging scale to assimilate the SST, SSH, and the in-situ observation of temperature and currents. This presentation focuses on the evaluation of model performance by comparing NICOPS outputs with observations and outputs from the existing NOS operational forecast system, OFS, that include New York, New Jersey, OFS NIOFS, Chesapeake Bay, OFS C-Box, Delaware Bay, OFS D-Box, and Gulf of Maine, OFS GOMOFS. These all include in the NICOP computation as shown in Figure 1. NICOP is FVCOM-based unstructured grid. C-Box, D-Box, and GOMOFs are ROM-based structured grid, while NIOF is PROM-based structured grid. Cross-model comparison show for water levels, NICOPs perform similarly well with the existing OFS. It is slightly better than GOMS and NIOFs, but slightly worse than C-Box, D-Box. This is likely due to the fact that the NICOPs open boundary is further offshore. C-Box and D-Box open boundary are close to shore, and also the value adjusts from the observations. For water temperature, NICOPs without data simulation has similar scale as existing OFS, while NICOPs with data simulation significantly outperforms existing OFS. For water currents, NICOP has similar scale with the existing OFS. This is based on the very limited analysis at a few available stations output from existing OFS. Overall, NICOP performance is significantly improved with data simulation, so the NICOP has a highly potential possibility to replace the 4 existing OFS. Yeah, Thank you. That's all for me.
Thank you. Next will be Zhuguang Wang, Understanding Sampling Air Characteristics and Ensemble-Based Estimates of Land Atmosphere Coupled Background Air Covariances in a Dryline CI Case Study.
Can you see my screen and hear me?
We can hear you. We cannot see your screen.
You'll need to share in Zoom, so just click the share button and try sharing your tab.
What about now?
No. You'll probably need to click OK. We can probably jump into virtual green room and do a little debugging, so we can move on to the next presenter.
All right. The next presenter will be Fei Yi, Empowering Communities through Flexible and Semi-Automated 3D Coastal Modeling and Stoff's 3D Atlantic.
Okay, thank you. Can you hear me? I'm trying to share my screen. Can you see my screen now?
Yes.
Okay. Hi, I'm Fei. I'm from Virginia Institute of Marine Science, and this work is a collaboration between VIMS and the NOAA Office of Coast Survey. Here I'm presenting a Stoff 3D Atlantic, which is a operational forecast oriented on the compound flooding for the Gulf Coast and the East Coast. Here we are focusing on making the setup of such a complex model more reproducible and make it cater to a wider basis of diverse users. So to do that, we built different levels of automation into the meshing, the model setup, and also the model evaluation and dissemination. So first, to resolve all those complex features, including the small rivers and levees in the coastal transition zone, we designed a few meshing tools, such as the river mesh tool, OCS mesh, which help us to automatically extract tens of thousands of small rivers in our model domain. Otherwise, this meshing work is just overwhelming for manual work. And if you zoom in, you can see all this complex river network in coastal Louisiana. It has many rivers of different sizes. Sometimes the river goes into a very narrow ship lock. And these river arcs are all automatically extracted, which helped us a lot. And for the automated setup, we have scripts that are publicly accessible on this GitHub website. And you can also access all the model outputs and visualize them using this so-called SIRA website. If you zoom in, you can see also the small rivers, complex river networks that resolved and simulated in this model framework. And we also constantly receive feedbacks and requests from stakeholders. For example, people from this coastal Louisiana region, they asked us to implement this so-called MTG river levee system, which is a very narrow levee, only 5 to 10 meters wide. And we were able to build this into our model mesh, explicitly resolve them using meter scale elements. And this turned out to be really important during Hurricane Francine 2024. With this levee in place, it can the model successfully predict that it can hold off the surge of Hurricane Francine. Otherwise, you would have more inundation.
Fei, I'm gonna have to cut you off. Thank you.
Yep. Yep.
All right, then let's go back and get Eunice Tabahi. Are you in here?
Hello, everyone. Can you hear me?
Yes. Fei,
Hello?
can you stop sharing your screen?
Yeah, yeah.
I think I already stopped. You still see my screen?
Okay, so hello, everybody. So my name is Yunus Sebe. I'm a PhD student at University Mohammed VI of Health and Sciences and member of Jihad Hub. So my process is about the new index in
Eunice,
the
can you go
yeah,
full screen?
full screen, okay. Now it's clear? Now it's okay?
No, we see your slide deck. You can try zooming in maybe. Or resharing.
Now it's okay?
No, we still see the slide deck.
Okay, I will share by using PowerPoint. Okay.
You can probably try resharing.
Yeah.
Yep.
Now?
Yes, we see it now. Thank you.
Okay. So my poster is about a new index in North Africa. Is the Sahara Ocean Index. It's look like North Atlantic Ocean Index and the Indian Southern Ocean Index. So my project is based on the analyze this index, how can interact with other climate indices in our region, North Africa, southern of Europe, and also east of United States. So we have the atmospheric and oceanic dynamics between our regions. So we started our project on analyze this index because the definition of this index is between the high pressure in Azores and low pressure in Miami. So I can show you here the definition of this index. As you can see in this map, the index is like the link between North Atlantic Ocean Index and the Mediterranean Ocean Index. And so in general, the data is based on the study, the Sahara Ocean Index and other climate indicators. And we found after that, the correlation after linkage between this index and other climate indices like North Atlantic Ocean Index, as you can see here. So we started to identify the correlation between this index and different many climate indicators in the world, and we focuses the first on the annual correlation, as you can see here in the table. So we found some significant correlation between Sahara Ocean Index and Oceano Nino Index, North Atlantic Ocean Index, and Western Hemisphere Polar. After that, we need to know more the patterns between our index and others in the seasonal lag correlation. And as you can see here, we found after this table and the heat map seasonal lag that this index is responsible of dust storms coming from the Sahara, because in general, our objectives is to identify this index because it's responsible of lifting dust coming from the Sahara. And after that, the future project is to create machine early warning system by using machine learning to reduce this impact of this index responsible of dust storms coming from the Sahara. Thank you.
Okay, we can go back to Wang. And we'll be sharing for her. Okay, Juan, you can go ahead.
Okay, thank you. My name is Xuguang Wang. I'm a professor of University of Oklahoma. and also director of cadre. Before I start, I'd like to acknowledge the first author, Aaron Johnson, and 3 NOAA collaborators, Claro, Mike, and Terrell. This is one of the 12 research trusts funded by cadre. Our eventual goal is to hopefully develop a strongly coupled land atmosphere data simulation system for the conventional line RFS for the conventional line RFS. This poster is addressing one of the challenges in doing that, which is to treat the sampling error associated with the limit ensemble members when we try to estimate the complex land atmosphere coupled error covariances. So we start with a CI case. Unfortunately, you cannot see my cursor. And one key experiment design is to create a mini test bed to house a few thousands of ensembles to provide a reference in truth. So this is done through cycling MPass and also using the ensemble dressing approach from Juan Bishop 2005. So once you create 1,000 members, you can develop various correlations you want. You can do this for like moisture, soil moisture with soil moisture correlation for the 3 different crosses, or soil moisture with model level 5 temperature for 3 different locations. And how do we quantify the sampling error? We have tried several approaches. At the bottom, you can see one approach. And you can see the black curve is the referencing correlation from 1,000 member. Red is using 10 member. Green is using the 90 member. Blue is using 30 member. So you can see for univariate correlation, soil moisture to soil moisture in B, the sampling error is increasing with distance. And if you look at the univariate correlation, that's not necessarily the case. The sampling error is actually the largest when the distance is close to 0. You also see a lot of uncertainty of the red curve showing, indeed, if you have smaller ensembles, you tend to have more issues or uncertainty in estimating the true covariances. Another approach is to calculate the minimum number of ensemble members to provide the reliable correlations. So the bottom figures at the bottom shows blue curve using the central location on the west of dry line. The other 2 is using the crosses at 2 other locations. You see at the west of dry line, you tend to need more members, showing more sampling error. If you pick a location near the dry line, you see within 50 kilometers, you tend to only need about 10 members, but beyond that, you need a lot more. So basically, we found the sampling error is highly flow dependent, is highly anisotropic, suggesting the great need of performing research to develop methods to treat the sampling error for the strongly coupled land atmosphere data simulation. Thank you.
Thank you. And our next presenter and our last presenter will be Huangju Yu, Upgrading Stoff's 3D Atlantic, a bias correction method for improved total water level predictions.
Yeah. Can you see my slide?
Yes.
Okay. Hello, I'm Hyungju Yu, a postdoc from Virginia Institute of Marine Science. Today's my talks follow the previous presentation about Stuff 3D, but focusing on improving its performance about total water level prediction at continental scale with a simple bias correction method. Stuff 3D already shows strong performance, but some biases remain. These mainly come from the DEM uncertainties and missing processes like thermal expansion due to the Busnesque approximation of the schism model. So to address this, we first analyzed the model bias across the about 140 NOAA tidal stations using hierarchical clustering analysis and principal component analysis, and we found consistent spatial temporal patterns of bias. Also, the important thing is that our model bias is strongly correlated with the observed thermostatic sea level, about 65%. So you can see the left side of the figure. Yeah, based on this finding, we apply the simple dynamic uniform offset to the non-tidal boundary condition and calculate from the prior 2 days. You can see the below figure. For example, we derive the bias from forecast number 0 to adjust forecast number 1 and continuously derive the bias from forecast number 1 to forecast number 2. So we test this method for 2 years. And now please look at the right figures. On the scatter map, the red dots mean improvement of RMSE and blue means the degradation. You can see that most stations are red, showing improvement with bias correction. The average improvement is about 2 to 3 centimeter, with some locally stations showing up to 10 centimeter. And overall, 80% of the stations achieved the RMSE below the 15 centimeter. Yeah, in summary, yeah, this simple bias correction makes top 3D more accurate and efficient, and it provides the better guidance for total water level forecasting in top 3D. Yeah, thank you for hearing my presentation. Thank you.
All right, thank you. And that will conclude the virtual poster slam. I want to thank all of the attendees and participants, both in person and virtual. If anyone has any questions regarding a specific poster, please feel free to reach out to either the speaker or us here at Epic, and we will get you in contact. And thank you, and welcome to UIFCW 2025.